Hello everyone, welcome back. And in this section, we are going to see it in code, how to extract keywords using sentence transformer algorithms and use diversity algorithms like maximum marginal relevance and max sum similarity. I connected the Google Colab notebook and also I mounted the drive. Now let's begin with our usual movie plot CSV, and we will import pandas and load it into the data frame just like previously. And let's drop some duplicates like previously again, and this time let's pick a different movie plot. So we are picking Interstellar, and just I'm printing the movie plot here. And as you can see, in 2067 crop blights and dust storms, this is the movie plot of Interstellar. And we are going to use Interstellar's movie plot and extract keywords from it and key phrases from it. So first things first, what we need to do is extract keywords or key phrases. So we are installing Spacy for the same. And using Spacy will extract noun chunks. In our case, we are not exactly using verb phrases, but for our case perhaps noun phrases is good enough. So I am using Spacy here, and from the movie plot I am just extracting the noun phrases. We are just passing through the Spacy model or whole text, and from that we are extracting all the noun chunks. And we are extracting the phrase corresponding to that noun chunk, and as long as there are no duplicates, we are just appending it to the candidates list, and we are returning that list here. So at the end of the day, these are all the noun phrases that are present in this movie plot of Interstellar, and we are extracting all of them. You can kind of assume that this is a coarse extraction where all of these are potential candidates for key phrases or keywords, and from these noun phrases we want to extract key phrases using sentence transformers library and the algorithms that we discussed. So we are just running the same, and we got the list back in this np_movie, which stands for noun phrases of the movie. Let's just print how many we have. Great, we have almost 174 noun phrases in this movie. And let's get started with our sentence transformer model. We are just installing the sentence transformers library here. Once the sentence transformers library is installed, let's download the sentence transformer model that we are using. And we have created a simple function here. All it does is that there is the whole document as well as there are potential noun phrases that you have. So this function returns the document embedding as well as converts every noun phrase into an embedding and returns that as well. Using this model, it converts the given document or phrase into a vector. All we are doing here is to use the transformer model and encode the text into a vector, and we are returning both the document embedding as well as all the candidate embeddings with this function. So let's run that function where we get the document embedding as well as all the key phrase embeddings. So we passed our movie plot as input and all the noun phrases list that we have previously collected, 174 items. Now what's happening here in this function or in this cell is basically since we have the key phrase embedding and document embedding, we are getting the cosine similarity of every key phrase embedding compared to the document embedding. And as we have seen previously, what we are doing is just sorting the cosine similarities in descending order and extracting the corresponding key phrases, and just we are collecting them. That's all that is happening here. So here we are just printing word doc similarity. This simply means all the noun phrases and their corresponding cosine similarity when compared to the document, and we know that there are 174 of them. And this is the sorted cosine similarity list, where among 174 words, the highest cosine similarity words cosine similarity is 0.94952, and the next one is 0.44, etc. So we are ordering in the decreased cosine similarity, and all we are doing here is collecting the sorted keywords based on their highest cosine similarity. We are collecting the words and we are just appending that in sorted keywords. As you can see, Cooper has the highest cosine similarity, and Cooper ship is the next one, then former NASA pilot, Murph's dust covered bedroom floor. So this is these words are in the descending order of cosine similarity, and we have 174 of them. So these are the noun phrases that we extracted previously, but now we have ordered them in the descending order of their cosine similarity compared to the full document, that is the movie plot vector. And as I mentioned, we have seen both the algorithms, maximum marginal relevance as well as max sum similarity. And again, thanks to keyword from Martin, from which I have taken these functions, and simply this function right here calculates the maximum marginal relevance, MMR. And what's happening inside the function, we have already discussed that, which is iteratively we'll extract keywords, and depending on lambda value that you have, that is the diversity value, you can strike a good balance between how close the extracted keywords are with the original document vector, as well as what is the intra cosine similarity between the words. Now let's call the function MMR, to which you are passing the document embedding, that is the vector of dimensions 384, and it's just one because it's the whole document. Then you have key phrase embeddings, which is of each key phrase is of dimensions 384, and you have 174 key phrases, and these are the embeddings. Now you need to pass in the corresponding key phrases, because you need to know, after sorting, you need to find the index that corresponds to the actual key phrase, not the vector, and return that, right? So that's why we are passing this. Note that to this MMR algorithm, we are not passing the sorted list. We are not passing the cosine similarity sorted list like you see here. We are not passing sorted keywords, because MMR algorithm internally calculates depending on the keyword diversity lambda that you give. It will only calculate. All you need to give is any list of keywords and their corresponding embeddings and the whole document embedding. And let's just run this. As you can see, it extracted 5 keywords that are very, very diverse. So Cooper is the first one, then we have 5,000 frozen embryos and anti-gravitational propulsion theory, then you have crop blights, then you have Murph's dust covered bedroom floor. These are the top 5 key phrases that we extracted from using the MMR algorithm. But if you want your distractors to more closely resemble the original document vector, then you can change this diversity value closer to 0 or away from 1.5. Let's run this and see. You can see that now it's much more in line, that you have Cooper, Murph's dust covered bedroom floor, former NASA pilot, dust patterns, Professor John Brand. So you can change this diversity factor from 1 to 0. As I mentioned, 0 means all the vectors are very close to the original document. So essentially keeping this to 0 will result in just the sorted list that we already have. But if you just increase it by a little bit, then you'll get more and more diversity. So you can play around with this to see which perfectly captures what you're looking for. But the thing to remember is that you can change this diversity factor and control how close you want these keywords to be similar to the original document. And the next one is max sum similarity. You can pass to max sum similarity the number of keywords that you want to extract, and you can also ask where you want to limit the list to. So here it says that from all the 174 keywords, sort the key phrases such that or keep only the top 20, and from those top 20 extract top 6 that have the maximum diversity among themselves. So that's what this code does. Let's run this. Awesome. So we got 6 key phrases, and what we did was to consider the top 20 key phrases that are similar to the original document, from which we extracted the top 6 diverse key phrases. So here we are done with the keyword extraction and diversity algorithms. Now let's come to finding similar documents. So if you remember, in our TF-IDF lesson, we have built a similar movie plot finder, which is given any movie plot, you would convert that into a large vector, and similarly all the movie plots are also converted into large vectors. Now we find the cosine similarity between those vectors to find the most similar movie plot to any given movie plot. Now let's do the exact thing using sentence transformers, not TF-IDF. If you remember, TF-IDF vectors are very sparse, for example 50,000 or 100,000, and the beauty with sentence transformers is the vectors are shorter, 364 dimensions or 380 dimensions, etc. You can find cosine similarity the same way and extract the most similar movie plots to a given movie plot. Let's get started with that. Again, now we are using Batman Begins, and once you have Batman Begins, again extract document embeddings as well as plot embeddings. What does this mean? Simply use the sentence transformer model, pass the Batman Begins plot, and pass all plots. All plots here means all the movie plots that are there, which is 3379. Convert all of them into a vector and convert Batman Begins into a vector. That's what this function is doing. It will take a little bit of time because we have about 3379 movie plots, and we need to convert everything into a vector using sentence transformer model. So it's just going to take a little bit of time. Awesome. It took a few minutes, probably 5 to 10 minutes. You can definitely fasten this process, and you can pre-compute these embeddings and store them as well. I just kept it there for simplicity, but we'll pre-compute and use them in the next section, where we are going to deploy this similarity algorithm into our Streamlit dashboard, moviepro.ai. And again, what we are doing here is simple, which is we are calculating the cosine similarity of the Batman Begins, that is document embedding, with all the plot embeddings. And once we get that, we are just sorting in the descending order of cosine similarity, and we are just printing our plots along with the movie names. Let's run this and it will be clear for you. Just like for sanity reasons, again we kept Batman Begins as well in the total list. So this is the top matching. If you search with Batman Begins, you get back Batman Begins. And then the next one is Dark Knight. Amazing. And then we have Lego Batman movie, Batman vs Dracula, Batman the Killing Joke, birds of prey. Perhaps we have Gotham City and other things. That's the reason why we got this. But simply put, you can use sentence transformer algorithm and do similarity search for movie plots like this, which is simply you compare the vector of a given movie plot with all the other movie plots and just sort them in the descending order and get the top n, and that's about this. And oftentimes this is quite superior to the TF-IDF algorithm, because we have seen with TF-IDF the shortcomings, and there is semantic similarity that's compared here because of dense vectors. Great. And just to recap, we have extracted our interstellar movie, and from the movie plot we extracted all the noun phrases using spaCy, and we converted all the noun phrases as well as the whole movie plot into vectors using sentence transformers. Then we found the most similar vectors and ordered them in descending order. Now in order to extract diversity, we use two different algorithms, maximum marginal relevance and max sum similarity. And if you are wondering where this code is taken from, both the MMR algorithm as well as the max sum similarity algorithm code that you see here is taken from KeyBert library, which is developed by Martin. So you can go ahead and explore KeyBert library more and look at various algorithms or code pieces that are present there. And yeah, so that's how we extracted our key phrases as well as introduced some diversity using two different algorithms. Thanks for watching.